My name is Katharine Jarmul, and I want to thank all of the organizers here and everyone helping for both inviting me here and allowing this presentation to happen. It looked a little dodgy for a while because I have an American passport, and that doesn't always make things easy for me. But I'm here, and I'm really glad that I'm here. My company is called Kjamistan, and you can check out, we do machine learning consulting work and other data science consulting work, and I'm based in Berlin, Germany as of 4 years ago. So when we talk about machine learning and we talk about interpretability in machine learning, who here has used machine learning as a service or is thinking about using machine learning as a service or maybe even builds machine learning as a service? And I'm not necessarily against this, but when I first started hearing about all of this machine learning as a service hype, I thought of this practical dev, which is writing code that nobody else can read. The byline being, does it run? Just leave it alone. And I feel like there is numerous machine learning as a service platforms where it's kind of like, just trust us. We're Google. We've figured out, we've solved translation, so don't worry about it. And that's not exactly the case. So even if you've solved something like sequence-to-sequence translation for 95% of the space, you have not solved it for probably the 5% that most users need. And this is what we would call, a state-of-the-art problem in research, in the sense that state-of-the-art might have solved the space, but the last 2% that's left is the actual practical implementations that you need. And so I would say when you choose machine learning as a service, you need to definitely be aware of the fact that you can't see the code and that you can't see the pre-processing on the data, and you perhaps can't even choose what modeling is used for your eventual end product. And these are all problems and complications that we'll talk about. And today we're going to really focus a little bit on the theory of interpretability, but also on these practical aspects. So how do we practically understand and interpret models, and maybe even models that we can't see the code of? How many people here have heard of adversarial learning? Okay, so just in case you haven't heard, adversarial learning is essentially a way that you try to fool machine learning. And adversarial learning began with a really nice piece of work by Andreas Karpathy, who is head of AI at Tesla. And about 2 or maybe 3 years ago now, he decided to start exploring how easy it was to trick recursive neural networks. And he used his paper to, he and the fellow researchers used their paper to describe that it was quite easy to trick machine learning networks. There's a lot of different theories on why this is possible. Some people say that there's linear interpretability between the different network layers, and that you can usually use this to easily trick just one of them into misclassification. Other people say that there's neural network blind spots, and that there's sections of the neural network that we can then fool or activate into an improper classification. But regardless of actually why this adversarial learning works, we can take a look here. This is a recent paper called Deep Explorer, and it allows you to find adversarial examples fairly easily. So nearly anybody can use this implementation, which is in Python. And what we have here is they tested the NVIDIA Dave 2 self-driving car platform. And we can see on the left-hand image that we're going to have a great day, and we're just driving down the car or driving down the street in our Tesla, and everything's working fine. And then we see in the right-hand side that we're probably going to have a pretty bad time. And depending on what is over that rail, we might die. And this is actually the exact same image with a different tint. So all that's changed is that the image on the right is darker. That's it. And when I started reading this paper, and also when I look at a lot of adversarial examples, I think as an engineer and as a machine learning practitioner, I want to understand why number 2 happens. I know some reasons for that, or some use cases where I can fix number 2. I can give it more training data. I can find ways to generalize. I can pre-process all of my image so that they have the right grayscale. These are all things that I can do, but I also want to know why my model is telling me to drive off the side of the road. We can hypothesize as humans, and we can say, perhaps this sign that's telling us to go to the left, perhaps it's misclassified. Maybe Somehow it sees something in the other section, in the section off the side of the road, but we don't know unless we can actually understand and interpret our models. And until we can do that, then we have a long way to go until I get in a self-driving car, at least. So why else care about interpretability? I will give you a few more examples in case you are not yet convinced. First is, as an engineer or as somebody that's in charge of production systems, you want to be able to know and explain what's in production. And it's a system that you control whether or not you built it. You want to be able to explain when it's behaving properly and when it's behaving poorly. Number two, your users, or potentially government institutions, are likely going to ask for explanations. So if you have any users in the EU, then you might have heard about GDPR, which is the General Data Protection Regulation. I have given a few talks on this recently, but one of the things that it does is it allows people to be informed about what automated processing is happening for them. And automated processing means machine learning. So if you're doing machine learning and some people in the EU use your application, they have a right to ask you and they have a right to be informed of what type of automated processing you're doing as of May 2018. Now, I'm not a compliance expert nor am I a legal scholar, so I'm not going to really argue about that. But also providing your users with some justification for why a decision was made about them can be useful because it can give you good feedback for your model. So what we want is labeled data. One way that we get labeled data is we ask users to label it. And one way to do that is to say, hey, I think this because I have this other piece of information. So for example, I recently had a few friends have babies. I bought them baby gifts. I used Amazon. Sorry world. I used Amazon because I forgot until the day before. Anyways, I used Amazon. And Amazon for weeks has been recommending me diapers, baby food, all sorts of other things. I am not with child, I don't have any kids. So for me, this is not a great recommendation, but I completely understand why it's the case. And if I could give feedback and Amazon asked me something like, hey, I saw that you recently bought a few baby gifts. Is this for you? Is this suggestion useful? Can you give me a reason why? If they gave me a few explanations of why they were making an inference about me, and I could tell them, no, that's actually not the case, and here's some other inferences you can make, then that's good feedback for the model, and that's something that they could then use to make better predictions. And finally, you ask for interpretability because you want to know when something's broken. So a lot of times, like for example, for the self-driving car, NVIDIA Dave 2 algorithm, it's like, it looks great. If it's a sunny day at noon, it looks great. But how do we infer how it's going to behave on a snowy day, on a rainy day, at night? These are all things that we need to know. And if we ask for explanations and we give difficult examples, we can start to figure out when and how it's broken. So hopefully now we are all like, yes, Katharine, interpretability is awesome. I want to have it and use it for all of my things. The first problem that we come across is how we define interpretability. So there's a great paper that we're going to be actually talking about one of the libraries around, and it's called Why Should I Trust You? And it's about model interpretability, and they actually open sourced a library we'll be talking about shortly. But it's by Marco Ribeiro and a few other researchers at the University of Washington. And they explain and define interpretability in a really useful way in their paper. They say, the notion of interpretability also depends on the target audience. Machine learning practitioners may be able to interpret small Bayesian networks, but laymen may be more comfortable with a small number of weighted features as an explanation. So your audience matters in the sense that if your audience is your data science team, you can likely deploy a fairly complex Bayesian network or something else, maybe even a random forest and so forth, and you have some inspection, some interpretability. But if you're talking to a doctor or a lawyer or a banker, they're probably not going to want to talk with you about priors, right? So you need to think about your audience when it comes to interpretability. And you need to think, who do I have to explain this to? And how am I then going to go about explaining it in a way that they can understand? And maybe you have to explain it a few different ways depending on your audience. Cognitive science comes into play here. So cognitive psychology is, of course, a long history of study. And we have Miller's Law. Who here has heard of Miller's Law? Okay, cool. And Miller's Law is essentially a thesis, a hypothesis that has been proved via numerous experiments that the human brain can only hold, essentially, to equate it with computing, we have 7 slots for RAM. And we can only hold these 7 slots for RAM, and it might be plus or minus 2, depending on the size of the objects, but we only have space for that many things to make a decision about. So when we look at how we explain things, we have to think of our own cognitive limitations. And in the paper that I was referring to, or actually that I will refer to in a minute, they actually are talking about how can we use the fact that we have only these 7 slots, or perhaps 9 at most. How can we use essentially a very dynamic feature space and reduce it into 7 explanatory features? And this is one area of very active and open research. Which leads us to testing interpretability. So we have a lot of tests in machine learning for scores, for accuracy, for precision and recall. What we don't have is we don't have a good score yet for interpretability. And of course, it's going to vary a little bit depending on our audience. So it might be difficult to come up with a global score. But one paper, which I highly, highly recommend reading, is Towards the Rigorous Science of Interpretable Machine Learning. And I believe that it was part of NIPS this year. And the researchers said that they would prefer application-grounded evaluation. So application-grounded evaluation involves conducting human experiments with a real application. If the researcher has a concrete application in mind, such as working with doctors or diagnosing patients with a particular disease, the best way to show that the model works is to evaluate it with respect to the task, doctors performing diagnoses. So this means we need to actually work with interpretability in a real use case. And the researchers here, they were working on a series of Bayesian networks that would explain pneumonia and would help diagnose pneumonia. And they did some research back and forth with the doctors themselves saying, okay, is this actually interpretable in the sense if I give you this type of explanation, if I give you that? And they tested the doctors on a few different ways of explaining interpretability and then making some evaluations on what worked best. Here is their diagram, which they call the taxonomy of interpretability. In the very bottom level, the most simple, we have functionally grounded evaluations where we create a series of tasks. And you can see these tasks like a lot of machine learning tasks that we would do and evaluate ourselves on. This is essentially just some user-based testing or QA testing for our machine learning. And we go all the way up to the top where we're doing this application-grounded evaluation with real humans on real tasks and getting real evaluative and maybe even survey-driven feedback. Of course, as we go up the taxonomy, it gets more costly and it gets more specific. So whether this is generalizable for every machine learning interpretability problem is to be debated. But particularly if you're doing something where a human needs to make a decision based on your model, you should be thinking about how to do these application level evaluations. So we're going to move out of theory and into practice. So I'm going to go through 3 case studies. And in these case studies, we're going to evaluate a model, and then we're going to determine how to interpret or allow for interpretability of that model. We're going to start with image recognition. Who here works in computer vision? And so CNNs, or convolutional neural networks, have come with a lot of advances. And some of these advances allow for us to see into the network. You've probably seen Deep Dream and other examples like that where you can see what the neural network sees. Now it's to be debated how much of that is us recognizing our own patterns and not, but we'll get into that in a minute. But image recognition is definitely fairly advanced when it comes to explanations. So what we're going to do is we're going to take a look at a library called LIME. And this stands for Local Interpretable Model Explanations. And with LIME, which is by the researcher group from the University of Washington, you can actually pip install it right now. It's a Python library. And with LIME, what you can do is you can ask for image explanations. And what the image explanations are going to do is it's going to take an image that you give it, and it's going to come up with a series of clusters of pixels. And those pixel clusters is going to try and find the smallest cluster of pixels that explains the classification. So I'm using Inception v3, which is a commonly used image classification model. It's trained on approximately 1,000 classes. And it's, I think, originally from Google researchers, but it's kind of was the state of the art maybe a year and a half ago or 2 years ago. So I decided to give it this Monty Python image of the black and the white knight, the black knight without his arms, and to ask Inception, hey, what is this? Any guesses? Did it properly classify anything? Anyone who's worked with Inception before? Okay. It thought it was a 20% chance that it's a rifle, 6% chance that it's a Doberman, the dog, and a 5% chance that it's a guillotine. At least guillotine is like right era, right? I was like, okay, something's going on. And, you know, I was like, okay, I wonder what's happening. So I decided to put it into LIME and ask for some image explanations. Does anybody want to guess what area of the image is a rifle? The sword? All right, survey says that's rifle. So, but I also thought so. I was like, okay, it's reasonable. It's in somebody's hand. It's, you know, a weapon, so maybe. But when we see patterns, right? We're humans. We're really, really good at pattern recognition. This is how we've evolved. But the computer is just like, yeah, sure, that makes sense. That's a rifle. So when we actually ask the computer to justify, or the model to justify itself, we see perhaps it's a little off. Where is the Doberman? Guy in the middle. Yes. That's the Doberman. So yeah, we can see, again, that LIME is using these clusters. And the way that I asked it is I set it to just use 2 clusters. You can ask for more or less clusters depending on it. And what it's going to do is it's going to find the highest percentage of probability of that classification within the image. And it's literally just going to pass these sections of the image through the same classification. All right, any final guesses for the guillotine? That's a guillotine. So, I mean, I know that some people believe in the singularity and stuff, but when I look at stuff like this, I'm like, oh man, we have a long way to go. So, but the cool thing is that LIME makes this really easy. This is literally to ask for the explanation, and you merely need to create an explainer object. I pass in the image, and it's going to create the clusters of pixels for me, and it's going to pass it through this algorithm. So let's go a little bit more into depth of how it works. This is a theoretical version of how it works. Depending on what model you're trying to use, it may or may not actually go like this. But here we have our function space. And in our function space, we have a 2-class problem. We have the red X's and we have the blue circles. And so this is our function space, and we can see it's nonlinear, and we can see that it's fairly difficult to define and interpret for a human. What the algorithm essentially will do is we're going to try to define that red X. And to define that red X, we're going to take samples around the red X, or like we saw with the image, samples within the red X, and we're going to try and find something that we can locally evaluate. We want to find a local interpretation that is true to our class system. And in doing so, we sample a few of the spaces around the X, and we decide that we can form a derivative or a function that explains just that local point. Now, this is not globally interpretable. This is not going to hold for any type of class on the other side of the equation. But what it is going to do is it's going to give us some explanations for that very small local space. And these local approximations, you can think of them as, end up being really useful for explanatory work. And this has now been used, as you can probably imagine, on regression problems, and Lime is trying to further expand the ways that you can use it. But you can pip install it today and start working with it and have fun with some inception problems. It's always a good time. Moving on from images, let's go to something else. Let's go to linear regression. We're going to talk about Kaggle. Who here is a Kaggler? Yay, Kaggle. It's fun. It's machine learning competition. But it's also really known for a lot of cool cheating that you can do. And I call it cheating in a loving sense. In a sense that you can really feature, engineer, and boost the hell out of a problem and get the highest score and have something that's completely uninterpretable and about as far from ground truth as you can be. But you can win the competition and make money for that. So I have no problem with it. It's just I have a problem when people use Kaggle at work, Kaggle strategies at work. So you might think linear regression, like this is a solved problem space, right? Right? Yep. But then what I'm going to take a look at today is linear regression with XGBoost. Who here has used XGBoost? And it's really awesome, right? Is it interpretable? Yeah. So we're going to take XGBoost and we're going to take an XGBoost regressor. And we're going to take a Kaggle case study that is near and dear to many Kagglers, which is the house prices regression problem. And this is one of the welcoming problems when you sign up to the site. This is available for you. You can either do Titanic or this one or any of the active ones. And Titanic is boring, so of course you do this one instead. And what it tries to do is predict house prices in Iowa. I don't know why Iowa. I don't care about house prices in Iowa, but this is what we do. And it gives you 79 features. And these have all been cleaned and pre-processed for you. And your goal is to predict house prices in Iowa given these 79 features. Now, because it's an introductory competition, a lot of people have open sourced their solutions. This is because they use it to say, oh, I'm really great at machine learning, please hire me. One such solution that I found, I wanted to find one that was performative, I wanted to find one that had a lot of feature engineering, and I wanted to find one that used XGBoost. And I found DJ Vine or Divine, unsure how he or her likes their name pronounced, but they had theirs up on GitHub, and it was fairly performant. It would have landed itself within the top 300, which is pretty good for a Kaggle competition. So I said, okay, this is great. It had a lot of feature engineering. And I'm like, okay, I'm going to use this, and I'm going to reverse engineer and try to explain what's happening within this and try to simplify it until it is the smallest explanatory space that I could use. So here we go. The library that I'm trying to use is called ELI5, or Explain to Me Like I'm 5. And ELI5 is another Python library that's available for you to pip install, and it works with XGBoost. So it works with both XGBoost regression and XGBoost trees, which is pretty cool. And what it can do is it can take a look internally at the model weights. So I just passed in the model, and here are my model weights. Oh my God. So I'm looking at this, and I'm like, okay, we have X7. X7 is a really great feature for a house. It's pretty awesome. X4817 is a pretty bad feature for a house. And we have polynomial features. So this is a common transformation that you do where you ask for a polynomial to represent certain sets of your features, and then you can essentially replace your features with these polynomial representations, which usually are fairly powerful for Kaggle, but pretty awful for interpretability. So I removed the polynomials. I said, okay, let's remove that part. And let's just get back to feature names we can actually read. And we see that the weights have changed, so the weights did change overall. But we also see quite a lot of duplication. So this is common in Kaggle when you're feature engineering to try and boost signals of something that is meaningful. So we see we have simplified overall quality, we have simplified overall qual, we have exterior qual and exterior first whatever it is. And we see that we have some repetition. We also see that at the bottom, I don't know if it's readable, but here it says 336 more. So it has all of these features and then 336 more. There is no way that I'm going to be able to make something explainable out of something with 360 features or so. It is just not going to work. So I said to myself, all right, thankfully I have my explanatory model, and I can perhaps then remove or reduce the feature space. So it's common in Kaggle to want to increase the feature space. This is also really common with the way that you would use ensembles, and you essentially average over a bunch of features, and this gives you, essentially regularization. But what I was curious about is, could I reduce the feature space and retain some level of performance? So I removed a bunch of features. And I removed features by using the weights from the previous slide. So I was able to use the weights here, decide what a good breaking point was, which seemed to be around the mean of the overall weights, and I reduced it to a set of 64 features. These 64 features, we can see, still have some of the problems. So I see that we still have derivative features. So we still have features that are derivative of something else. And what I would probably do next at this point in time is start deciding how I can either average or remove them. But let's just move forward. How many people here, so I was somewhat satisfied with this level of simplification. I have 64 features. I can likely, via correlation, reduce that further, at least reduce it when I explain it to a person further. And I could actually potentially use this. I could say, hey user, if you improve your fireplace, you might be able to sell your house for 5,000 more euros or so forth. So how many people here think my model outperformed the original model? Oh man, you guys have no faith in me. How many people here think that it performed about the same? And how many people here think it performed worse or even a lot worse? Okay. So here is the comparative model performance. This is ranking, and this is the overall score. Now, unfortunately, it looks, I have a histogram that I can also show you, because obviously we have some outlier teams here that have done really poorly, and they have screwed up our graph. But the original score was 0.07 higher than mine. And on the overall, this was not a massive scale difference. So it scored around 400. My ranking was around 800. And if you do the overall, so this is a mean squared error, logarithmic, I believe. If you did that, the percentage of error that you added was probably about 3 points percentage of error. So I added 3 percentage points of error or so. It can be debated exactly how to interpret that, but it did not do massively poorly. And this is a great reduction and change to the model. I would argue, too, that the added explanatory benefits are something that if you were actually building a competitor to, say, a real estate platform, that the added explanatory benefits and the added benefits you can say of here's exactly how much it would be worth for you to do this renovation is something that you could likely add as a feature to your site. Moving on to our final case study. And this is a case study of natural language processing, which is something that is indeed very, very near and dear to me. So natural language processing is something I normally do as part of my consulting work. And I actually created a course on DataCamp, which is a data science platform. And in it, we built on natural language processing fundamentals. And as the final case study of this 4-chapter piece of work, I decided to study an NLP problem. And the NLP problem was fake news. So fake news is a very hot topic in NLP today. I think it's kind of funny because fake news has been around for a long time. This is some fun Hillary Clinton fake news from another era. That Bill is catching Hillary with a space alien. And I remember growing up, often in the checkout aisle, they would sell these tabloids that are, of course, full of fake news, and Dick Cheney is a robot, and all sorts of really fun things. And now it's just moved online, but fake news is nothing new. And it's a really big source of research and debate within the natural language processing community because, unfortunately, it has some very real consequences. Donald Trump. Anyways, outside of the very real consequences, though, when we think about the problem space, if we can fool a human, are we going to be able to build an algorithm smarter than a human? It's a really big problem, right? And even though I decided, okay, this might be fun data set to play around with, I was not hopeful that I would have a very good success rate or a very good score. Because clearly, if we can make news headlines that fool a person, it's going to be very, very difficult to program any type of machine learning model that is more intelligent or even half as intelligent as a human, right? So this is a very difficult problem space, and there's a lot of good writing on it right now and research. But I had come across a blog post, and there was this person, and they had said, I built a fake news classifier. Here's the data set I used, and I got 95% accuracy. I was like, okay. I want to play around with this data set and see what's going on. So I did. And I created some TF-IDF vectors and some count vectors, which are essentially just encodings for words. And I did it on a token level, which is just a word level. And here's my ROC curve. So if you don't do machine learning, you might not know, but this area right here, that's where you want to be when it rises. And so I was looking at this. I used a few different common, very easy to interpret scikit-learn models, including multinomial naive Bayes, passive-aggressive, and linear SVC and SGD. These are fairly common within NLP space, especially when you're using word encodings. And so I'm looking at this, and I'm like, oh, yeah. I'm going to be like a cajillionaire. I'm going to sell my model to Facebook, and yeah, I'll buy everybody shots of vodka later or something. Anyways, I was thinking to myself, yeah, this is awesome. But no, I was actually thinking to myself, there is something seriously wrong with this data, because there is no way that I'm going to score this high with very, very little pre-processing and very, very little feature engineering. So I decided to take a look at what's going on in the models. And this is fairly easy to do, especially when you have a two-class or even a multi-class problem, and you have these linear equations. What you can do is you can take the weights. I took the weights of the top real and the top fake tokens, and then I was able to average them across all of the performant models. And here are the top real tokens: SED, Cruz, Tuesday, Conservative, GOP, and Islamic. Yeah. So, not very impressive, right? Not really telling us much about real news. I will say that SED, or derivatives of the word to say, when I used lemmatization, which is a way to, across verb tenses to make the same stem. So I will say that to say definitely was an outlier in the case of signal. And we can think of this in the fact that when you are a journalist and you're writing, you'll often say, Hillary Clinton said, Donald Trump said, Angela Merkel said. This is how you usually quote people. And so there was a very hard signal, or a very high signal, strong signal, within real news of the word to say and its derivatives. But unfortunately, the fake tokens, and I feel like some are cut off here, are 2016, share, print, October, and I believe it was November after that, and something else, like Hillary at the end. So yeah, clearly I have not built a very good fake news detector. This is garbage. I can't use this in any meaningful way to detect fake news. But if I had looked at this, I would have thought, oh yeah, no problem. I solved a fake news problem. When I actually introspect, I see that I'm very sad. This is because I have not solved fake news, and also fake news is a really hard problem. So what can we potentially take away from this? Machine learning, the first and foremost takeaway is I want that machine learning interpretability is real. This is something that you can actively do and work on, and it's something that's important, in my opinion. Depending on the black box that you're talking about, introspection and interpretability can be pursued. So we have, within Python, we thankfully have quite a lot of tools and libraries. There's even more research. I usually get forwarded at least one paper a day on new ways that people are using to introspect neural networks. We can talk a lot about RNNs because RNNs in and of themselves hold memory. This is something that we can use to determine what has been learned, or at least determine some signals for predictors. But introspection and interpretability is a worthwhile pursuit, and it can be pursued. Simplifying a complex model will likely reduce accuracy. This is just, we know this is how this works. But perhaps it's not by much. So I know a lot of companies that the first thing they do when they have a problem space is they try to think of the most optimized and complex solution to the problem using all of the newest and coolest tricks. But I would err and say, first build the minimum viable model. First build the absolute most simple and interpretable use case, and then further optimize on top of that. And if you do that first and then further optimize on top of that, perhaps you can find some good in-between where you haven't completely over-engineered your features and your problem space, and you can still explain it in some way, shape, or form. Finally, this is an open area of research. And if you're a researcher, or if you work in a research lab, or you're a student looking for a research problem, it could definitely use your help. You will probably get published in a bunch of places because it is also very hot right now. So it's a win-win, I would say. If you're not a researcher, but you are, say, a machine learning practitioner, these libraries need a lot of help. So for right now, what I notice is they're quite slow. They're not very performant, and this is something that I think the community can help with. They've also asked for some specific help in the area of rapid and accurate sampling. So if you have some experience with sampling problems, then you can likely contribute and really make the authors happy. And the more that we can make these usable, the more common I think it will be to also present on interpretability. Finally, what I hope that you take away is that interpretability can be useful, that this can be actually a bonus that you add within your machine learning where you can offer an interpretable explanation as something useful to your end user or to the end client. And I think that that's going to make your engineers happier, and it's hopefully going to make your users happier. And thank you very much. If you have questions, we have time.
Thank you very much. Very interesting. Questions? Oh, he was fast.
Hello. Thank you very much. This is very interesting topic. Very interesting talk. Can you just, by any chance, some numbers of what's the performance of the explaining weights of model? Just some of them, so I can understand the relativeness.
Sorry?
The performance, like how much time will take explaining one model by using LM5 or LIME algorithm?
Yeah, so LIME takes a lot longer. This is because LIME uses, we saw the type of equation that it uses, so it's going to create a set of samples, and then it's going to test each of those samples. And because I don't think that they're using anywhere near full parallelization, this can take a few minutes. It's not going to take a massive amount. Now, I have a GPU on my computer, so I generally also use GPUs for these problems, but I honestly don't think LIME uses the GPU at all. No, I don't think it does. So we're talking minutes, not hours. So, and for ELI5 and explaining the weights, that's nearly spontaneous. So it's nearly.
Yeah, and second following question. So as I understand, so LA5 or whatever LIME actually gives you weights of the features for built model. Yeah. Does it have any functionality to give you the weights of the data that came on the prediction in the prediction time?
Yeah, so you can also explain a particular prediction. So you can pass it a particular prediction, and as long as you have a complete feature set, then it will tell you, okay, for this particular prediction, these were the important weights.
Okay, thank you.
No problem.
Thank you very much for the very interesting presentation. So since I daily happen to have to make results of machine learning interpretable to people who don't even know what machine learning is, my impression so far was that the best compromise between flexibility and interpretability can be given by these decision trees. Do you think there is any way to make the representation more powerful by employing the result? So basically, in order to show us interpretability, you showed us lists of variables. Do you think there is a scope for like taking the result of a neural network or anything and building a tree that explains something better?
Yeah, so I definitely, there's a few different research papers that are trying to do exactly this, and I think that there's also this new movement of Bayesian neural networks, right, which are maybe slightly more interpretable than our current RNN architectures. I would say yes, there's a lot of movement and research in that. Can I point you to an exact tool? No. There is a library called scikit-learn expert sys, and what it allows you to do is create a Bayesian rule set for an already pre-trained scikit-learn model. So that might be worth exploring, but it's just going to create the same, like, if blah, 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 percentage chance, so-and-so. So it's probably doing exactly what you're doing right now, so I'm sorry.
All right, thank you. Another one.
On this LI5 example, when we get lots of features which were similarly named, it's very probably at least somewhat interchangeable. Like we can, and it would be a nice tool to have to cluster them into some groups and see those weights. Do we have something of like LI form probably?
Yeah. Unfortunately not. I think that would be really useful because I think it's fairly easy to test some level of correlation or covariance. But the problem is do we actually know that these are truly correlated, or do they just imply correlation? So like statistically, that's a difficult question. However, in this particular problem set, they are derivatives of the exact same field. So what we can do for this particular problem is remove them and just take whichever one has a better or more consistent signal. That's normally what I do, and I will continue to work with this model until I get it to probably far less performative, but very, very explanatory area. And there is indeed lots of different tools you can use for looking at correlation between features.
Thank you.
Maybe a related question. For me, this ranking of features is somehow similar to what PCA do. But PCA do is somehow from the different end. It's combine feature together, adding some weights for them, but we can still see, okay, the combined feature number 1, number 3, so contain these initial features in these proportions and can do some do some conclusions from this.
Yes, definitely. So anytime that we talk about a multi-dimensional space and we talk about dimensionality reduction, which is exactly what PCA and PCI and a few other therapies,
ICA,
yeah.
SVD,
Yeah.
TSNA, and the full zoo of things like this.
Yes. But what happens in this dimensionality reduction is we can sometimes get a more explainable signal, and that's exactly what the Towards Rigorous Interpretive Model paper is about, is how can we potentially use our own machine learning to talk about dimensionality reduction and allow for us to say, okay, here's the signals or the metrics or the measurements that are both human understandable and then also explain potentially a complex space. However, I do have to put a however for a moment, that I gave a slightly more theoretical presentation of this at PyData Warsaw a few weeks ago, and one of the problems with dimensionality reduction is depending on your projection space and how well you know your data, you can have very different viewpoints of the same thing. And so you can say, yeah, with this projection, oh yeah, look, we got this topic cluster right here, it looks very clear. Then you change the projection slightly, or you use a different algorithm, and it looks completely different. So
you can just change the initial seeds sometimes and see completely different thing. Yes,
exactly.
I agree.
So it's sometimes, maybe if you know your data well, great. But if you don't, you might just be rolling a dice, essentially.
Yes. Please.
There's nobody else. I have another question. It's probably a very naive question, but so if you see that two very correlated variables rank first and third, like in the house example, yeah, one possible reaction is, well, they're basically the same thing. I want to do dimensionality reduction. But my own reduction, probably because I'm just not used to this degree of flexibility of models, is I should take the difference and replace the other with the difference because it's conveying some information. Am I just stuck with linear word, or does it make any sense?
I mean, this is essentially what averaging trees do in a lot of ways, right? So like we find a cluster of features, and when we do like averaging random forests and so forth, then we are creating essentially like this is an average of these features that I see in some way as correlated because they end up on the same branch of the decision tree. So I think that like statistically it's sound. Does it depend on your data? Yes, of course.
Okay, thank you.